Alrighty, Physics 105. This is Chapter 9, Momentum. So here are the objectives. We'll discuss something called impulse, and we'll calculate impulse as the area under the force-time curve. We'll find the linear momentum of an object in terms of its mass and velocity, and we'll understand that momentum is a vector quantity. We'll learn the relationship between impulse imparted to an object and the change in the object's momentum, and that's called the impulse momentum theorem. We'll learn about the conservation of momentum. What does that mean? It means that the total momentum of an isolated system is the same before and after any kind of interaction. And then we'll learn about angular momentum and how it's conserved. And we'll understand the close similarity of these ideas with those of linear momentum. All right, so we want to talk about collisions. So collisions. And this is what we care about right now. We want to know the velocity of an object before and after a collision. All right, so here's a tennis ball being smacked by a tennis racket. So why does the velocity of the tennis ball change? Well, that's sort of obvious, because the racket exerted a force on it. All right, is the force that the racket exerts on the tennis ball, is that force constant? Certainly not. How long do the racket and ball interact? Is it instantaneous? Certainly not. Okay, here, ever heard of a gooseball? So this is a gooseball colliding with the floor. So it starts here, and it goes here, and it goes there, and then it goes back. All right. So those are nice photographs. So is the force that the floor exerts on the gooseball constant? Certainly not. I mean, here it's just barely touching, whereas here it's, it's a lot of it's touching. So the force is certainly not constant. Is the collision instantaneous? Certainly not. Okay, here's another example. So here's our cart from lab. This is the sensor that measures force. There's a magnet here. This is the cart that's traveling this direction. There's a magnet there. So what we're doing is we're making a graph of force versus time. So you start here and you shoot the cart to the right. And initially there's very little force. Then as this gets closer and closer, the force increases. Then the cart returns, and so the force decreases. So just look at that graph. Is the force constant? Certainly not. I mean, it's nothing, then it goes way up, and then way down, and nothing again. Is the collision instantaneous? Certainly not. Right? That's not instantaneous. All right, so now think of any kind of collision you want. Do all collisions vary with time? I think you have to admit, if you look closely enough, yeah, they do. Okay, so what we're saying is that the force is not constant. In fact, the force varies with time. With time. Well, if the force is not constant, of course, that means the acceleration is not constant. If the acceleration is not constant, can we use the kinematic equations? No. So now what are we going to do? So we can't use the kinematic equations anymore to solve our problems. So we're going to use something else, which is called the impulse momentum theorem. Okay, what is that all about? So here's that graph similar to the one I just showed you, force versus time. So this is some kind of a interaction, some kind of collision, and you can see that the force is 0, and then the force increases, decreases, goes back to 0, like the one I just showed you. And so the area under the curve is called the impulse. And for whatever reason, they use J for the impulse, all right? So J is the impulse. So the impulse is the area under the force versus time graph. Now, and you'll get to play with this in lab, and the computer will calculate that area. I mean, you know, if it were a nice rectangle, you could do it, piece of cake. But if it's some crazy thing like this, you really need a computer to do it. So the computer will give you that area. Now the impulse, it's also equal to some average force times the delta t. So in other words, if we say that this is delta t, then there's some average force where the average force times the time of collision would equal this area, which equals the impulse. Okay, now, why is it called the impulse momentum theorem? What's momentum? We haven't talked about that yet. So let's talk about that. So momentum, incredibly important in physics. Momentum, lowercase p, vector equals mass times velocity, vector. So that's momentum, okay? That's momentum, mv. So if we know that, we can write the impulse momentum theorem as differently. And here's why. So here's a different way to, so we have J equals F average delta T, and that's also, I'll show you later, that's also equal to delta P, which is just mv final minus mv initial. Okay? So this is another way to write the impulse momentum theorem. Okay, so there you go. All right. So impulse area under the force versus time graph, average force delta t, that's equal to mv final minus mv initial, which is delta p. So there you go. It's kind of a long thing, but that's how it is. So let's kind of review here. So here's a review question. According to F equals ma, and of course A is delta V over delta t, according to F equals ma, what causes a change in the velocity? A force, right? Because force equals mass delta V delta t. So if you have a delta V, you have to have a force. So forces cause a change in velocity. And you already know that, F equals ma. So force. But now, here's our new way of looking at things. According to the impulse equals delta P, right? J equals delta P. What causes a change in the momentum? Well, it's obvious, right? The impulse. Okay. So if you have a change in momentum, that means that there has to be an impulse. So basically, you know, we can't use kinematic equations. We have forces that vary. So we're just going to not really talk about that anymore. We're going to just talk about this impulse momentum theorem. And we'll do an example, and don't worry. But so now we're thinking of an impulse acting on an object, and if that is the case, that the object's momentum will change. All right, so here's the plan. We want to know the velocity of an object before and after the collision. We can't use kinematic equations for the collision because the forces aren't constant, so the acceleration is not constant. Now here's the beautiful thing. We don't have to know all the details of the force. All we have to do is be able to plot it versus time. If we can plot the force versus time, and then if we can measure this impulse, which is easy to do, you know, then you just use the impulse momentum theorem, right? So if you know the impulse and you know the mass, then you can figure out the velocity before and the velocity after. So that's really what we're concerned with, calculating the impulse. All right, now here's a question. A paratrooper whose chute fails to open lands in snow. She is hurt slightly. Had she landed on bare ground, the stopping time would have been 10 times shorter and the collision lethal. She would have died. Does the presence of the snow change the values of the change in momentum, the impulse, or the force stopping the paratrooper? I gave you some hints. So every student, please pause your video now and think about this and come up with an answer and, you know, use this. Okay, so we're back. So let's kind of draw this a little bit. So here's the ground. And let's say here's snow. Okay, and she's way up here with her parachute, right? Okay, and so basically here, that's the velocity initial, and when she hits and the final velocity is 0. All right, so that's with the snow. Now let's say there's no snow, so here's the parachute again, whatever. And this time the velocity initial is right before she hits the ground. Again, velocity final is 0. Now, we can make an approximation. We're going to say, that this distance here is really, it's large. Okay, it's very large relative to the thickness of the snow. So we're going to approximately say that this VI is the same as that VI. No, it's not, right? Because, obviously, if the snow were not there, I mean, it's free fall. Well, we don't even know if it's free fall because of the parachute. But basically, all I'm saying is we're going to say that this VI equals that VI, and it's close enough. All right, so the VIs are the same. The V finals are the same, right? She stops. So if the V initials are the same, that means that the momentum initial is the same. If the V final is the same, it means that P final is the same. If they're the same, it means that delta P is the same. If delta P is the same, it means that the impulse is the same. So that's the same, so this has to be the same. All right? But that's the whole point. So the question says, okay, so we have F average delta T snow equals F average delta T ground. Now, what does the snow do? It makes the collision last longer than it would if you hit just the bare ground, right? That's what it says. It says, had she landed on bare ground, the stopping time would have been 10 times shorter. So in other words, for the snow, the delta T is large. For the ground, the delta T is small. Well, remember, that times that has to equal that times that. Well, how does that happen? Simple. It means that this force is much, much less than this force, right? So there you go, all right? So what changed? The only thing that changed is the force stopping the paratrooper. And again, and the reason the force is less is because the time, for the collision with the snow is much, much longer than the time of the collision just hitting the bare ground. Make sure you understand that. That's kind of this is the essence of the impulse momentum theorem, so you really have to understand that. So this is pole vaulting back in 1904. So 1904, they didn't have fiberglass poles like they have now. I think they were bamboo, I'm not sure. But anyway, so when they did the pole vault, they just landed on sawdust. Well, thank goodness they didn't have fiberglass poles, and they couldn't go very high, because can you imagine landing on sawdust? Well, nowadays, we have all these super cool fiberglass poles and synthetic everything, and I wish I knew what the world record was back in 1905. I should have looked it up. It doesn't look like very high, right? Maybe, I don't know, 10, 11 feet, I don't know. Well, now the world record is over 20 feet. And can you imagine falling on sawdust from 20 feet? And so now they have these pole vault pits. And so what does a pole vault pit do? It makes the collision time very, very long compared to falling on sawdust. So therefore, the average force is very, very short. That's how it works. And you see the same thing for high jumping. All right, now we're going to do an example with this impulse momentum theorem. And this is a very long example. So when we do this in class, it usually takes half an hour. So we'll see. Maybe it won't take so long. So everybody read that, please. So this is basically how we're going to use the impulse momentum theorem to solve a problem. Okay. Okay, so you drop a ball, it falls to the floor, it bounces and it rebounds. The force of the floor on the ball, the normal force is shown below. So the normal force is not constant. So during the collision, you can't use kinematic equations. All right? So how high does the ball rebound? Oh, golly. So it sounds like a kinematics problem, right? You know, how high does the ball rebound? So we have to draw a complete pictorial representation. So here's the question you want to ask yourself right away. How many points do we need? Well, you know, we need the initial point, right? We need the final point, so it's going to, you know, it's going like, we need the final point, but how many points do we need on the floor? Well, we need 2, because we need one right before the collision and right after the collision. So we need 4 points on the pictorial representation. Oh my goodness. All right, so save a little time. Okay, so you know the procedure. Now this is only a one-dimensional problem, right? So we don't have to have x's, we just need the y's. So initial y velocity, y1, v1y, that's right before the collision. This is during the free fall, right? Well, we'll get to that, don't worry. This is y2, v2y right after the collision, and this is where it stops, right? y3, v3y. Okay, so we do what we do. So y0, 2 meters. We're dropping it from rest, so that's 0. Okay, y1 is 0, no kidding, right? That's when it hits the floor. We don't know the velocity right before the collision. Let's go here. y2 is still 0, it's on the floor. That's right after the collision. We don't know the velocity after collision. And then it goes here and it stops. So y3, that's the height. That's what we want to know. The velocity here is 0. And during the free fall part, you know, a equals minus g. Okay, and let me just repeat myself. This is the velocity before the collision. This is the velocity after collision. So we're going to have to use impulse momentum to calculate those. All right, so we want to calculate y3. So how are we going to do that? I mean, all we have to look at is from here to here. That's just free fall, right? So we're just going to use kinematics. Okay, so that's not bad. That's just kinematics. However, in order to calculate this height, y3, what are we going to need? We're going to need v2y. Now, this is the velocity after the collision. How are we going to calculate the velocity after a collision? Impulse momentum, right? We have to use impulse momentum. Oh my gosh, that's life. Okay, well, in order to use impulse momentum theorem, we also need to know what the impulse is, right? Which is, you know, the area under the force versus time graph, right? And we need to know this. Oh boy. Now, let's go back again. The impulse equals F average delta t, which equals m v final minus v initial. Okay. Now, we got to think about this, right? Again, this is area under the curve. All right, this is true, but we can also use area under the curve. Area under curve. Okay. How many impulses act on the ball during the collision? Well, you know, there's obviously the floor, right? I mean, they gave us that. So there's the floor, but what else? What else is acting on that ball during the collision? Gravity, right? Gravity. Well, what's the gravitational force on the ball? Well, you know, the weight is mg, and the mass is 0.2 kilograms. G is 9.8 meters per second squared. So that's 1.96 newtons. Okay? Now, so basically 2 newtons. You know, that's the weight. Now look at this. 480 newtons over 10 milliseconds. And this is just going to be 2 newtons over 10 milliseconds. So, is this a significant fraction of that? No. So, you know what we can do? We can ignore it. All right? We can ignore it. Now, if this were something like, 2 or 3 newtons, we couldn't ignore it. But this is almost 500 newtons. What's 2 compared to 500? Insignificant. So that's called the impulse approximation, where you just ignore gravity because it's insignificant compared to this. So we'll save a little time doing that. All right. And then, of course, all right, so kinematics, impulse momentum. Now, how are we going to get this? How are we going to get v1y? We have to get v1y in order to use impulse momentum theorem. Well, from here to here is just free fall. So we'll get v1y just from free fall, right? Just from kinematics. Whew! So that's what we have to do. All right? So let's do it. Okay, number 1. Let's calculate that v1y. So this is a nice problem because it sort of reviews what we've learned a long time ago. Okay, so first we'll calculate v1y. Okay, so we'll just use the third kinematic equation. So v1y squared equals v0y squared minus 2g delta y. And let's be a little careful. We have all these, we have y0, y1, y2, y3. Let's not just write delta y, let's write what it is. So delta y is final minus initial. So y1 minus y0. Okay, now what's v0y? It is 0, so goodbye. And what is y1? It is 0, so we'll put a 0 there. Okay, so therefore, we have v1y. We can take the square root, and we're going to insert a negative because it's going down, equals negative square root 2gy0. And what is that? Just plug it all in. I promise you, you get minus 6.26 meters per second. Okay, so that's the first thing. So, that's not a big deal, right? That's chapter 2. We all know how to do that. Okay, now, all right, so we've figured this out. Now we need to figure that out. Y, v2y. Okay, so again, so now we want v2y. Okay, impulse momentum. J equals delta p, which is mv2 minus mv1. All right, so let's see. So therefore, J, what do we want? v2y. So J plus mv1y over m2 equals v2y. So I did that right? Yep, okay. And all right, that's cool. And we can, we can rewrite that. That's the same thing as J over m2. Oh golly, what's that m right there? I hate when I do that. Oh no, just m, sorry. Okay, all right. That's just J over m plus v1y. Right? You can split this up into 2 fractions. Here you have J over m, here the m's cancel. Okay, so let's do it. So we need to know J. Well, what's J? So remember, J is the area under the curve. Now we don't need a computer to do that because it's a triangle, right? So J equals the area of the triangle. Area of the triangle is half base 10 times 10 minus 3 seconds times the height, 480 newtons. I promise you, you do that, you get 2.4 Newton seconds, right? Newton seconds. All right, so here we go. So J is 2.4 Newton seconds. Okay, the mass, what's the mass? 0.2 kilograms, 0.2 kilograms. V1y, where's that? Right there. So it's minus 6.26 meters per second. And I promise you, you do that, and you get 5.74 meters per second. Okay. All right. Okay. What did I write down? Okay, sorry. All right. So now we're finally at a situation where we can calculate y3. So let's do that. So, okay, so this is, yeah. All right, so now we can finally calculate y3. Okay, so yeah. Okay, y3, let's see, we know this velocity, we know this velocity, it's free fall, we know acceleration, we just want to find the height, so it's that third kinematic equation again. So it's v3y squared equals v2y squared minus 2g y3 minus y2. And let's see, v3y is 0, right? It stops. So that's a 0. And y2 is 0. So it's getting better all the time. All right, so therefore, just put that on the other side. So y3 equals v2y squared over 2g. And I promise you, you plug in everything that we have, 5.74, 2g, you get 1.68 meters. So that's the answer. Now, something very, very, very important. We dropped it from a height of 2 meters, right? And then, did it bounce all the way back up to 2 meters? No, it did not. It only went to 1.68. Does that make sense? Well, yeah, it makes sense, right? I mean, it wasted some energy when it hit the ground, when it hit the floor. I mean, what would you do if you came up with 2.2 meters here? That'd be nuts, right? That would require like a little rocket engine or something like that, all right? So you know this is going to be less than 2. Anyway, make sure you can do this because this is the kind of problem that you're going to solve using impulse momentum theorem. All right, let's summarize this. All right, so here again is the impulse momentum theorem. Impulse equals the change in momentum, which equals F average delta t. And okay, so if an object is brought to rest, delta p is blank. Whether the object collides with a brick wall, a bale of hay, or whatever. It's the same, right? It's the same. Okay, because the final velocity is 0, and we're assuming that the initial velocity is pretty much 0. So it's the same. Delta p is the same. So therefore, so that means this is the same. It means this is the same. However, if delta t is short, so if this is really, really short, like you're hitting the brick wall, what's going to be true at F average? It's going to be large. Simple as that. If delta t is long, like if you hit a bale of hay, so if this is long, then this will be short. So there you go. Oh, all right, that's a good place to stop.